Dear learner, welcome to today's lesson in your favorite TV channel, Hope Channel Kenya, in the segment, your favorite segment, Knowledge Quest. Our subject today is mathematics. I'll be your teacher, Mr. Mori Sylvester. Now, our topic today is matrices. As you can see, it's been displayed to you, matrices. It's a topic that is quite interesting to work on. And first of all, what is a matrix? So we're going to start by the introduction of what a matrix is. Now, matrix this matrices is the plural form of the word matrix. So I'll be using matrix occasionally or matrices. When I say matrix, I mean the singular form of matrices. Now, what is a matrix? So a matrix is a rectangular pattern of numbers. A rectangular pattern of numbers. So it can be an arrangement of numbers in rows and columns. Let's say, for example, so we have that arrangement right there, which is 1, 3, 4, 1, 3, 2, 4. Now the numbers have been arranged in such a way that there are rows and columns. Now basically a matrix is made of rows and columns. So a matrix is made of rows and columns. So when I say rows and columns, what do I mean? So rows are the horizontal arrangement of numbers in a matrix, which is these ones which go to the other side. So we call them rows, while the vertical arrangement of the numbers, this one right here, we call them columns. Now, a matrix can have more than two rows, more than two columns. It depends with the number of columns and rows right there. So what we know, what we call that is the order of a matrix. So order of a matrix. So when we talk of the order of a matrix, we're talking about the number of rows and columns that matrix has. Now take an example of the one that I've given. It has 2 rows and then it has 2 columns. So it is a matrix that has order 2 by 2. So this matrix has an order of 2 by 2. Which one comes first? So we write rows first. These are rows, and then columns. We have rows and then columns. Now, the numbers that occupy the rows and columns at their respective positions, we call them elements. For example, this one. So the circled parts of this matrix, we call them elements. So they are elements of the matrix. Now they can be in rows or in columns. Now depending with the matrix, with the order of the matrix, we can be able to say the position of that element in that matrix. So for example, we have this matrix here. Now we have this matrix here. Its order, we've said that the order of a matrix is given in rows and then multiplied by the columns. So in this case, it has 1, 2, 3 rows, and then we have 1, 2, 3 columns. So the order of this matrix here is 3 by 3 because it has 3 rows and then 3 columns. Now the elements, we can see them at their respective positions. So in case you are talking of a given element, you will address it as per its position. Its position to mean what? Its row and its column. For example, one here, this one here, it is in the first row and the first column position. Talking of these 3 at that point there, we're talking of 3 being in the 3rd row and then the 3rd column. So it is good to always note the position of an element in a matrix. talk of maybe this 5 here. 5, it is in the, so 5 is in the second row and in the third column. Always the rows come first and then the column comes the second. So after knowing how the matrix looks like, now we need to look at what we call addition and subtraction of matrices. I mean, basically operations on matrices. So number 1, addition and subtraction. Now, important to note that addition and subtraction of matrices is possible only when matrices have the same order. That is, they have, if it is 2 by 2 and we have maybe, let's have an example. If the matrix A has elements that is 4, 5, 6, 7, then we have B, which is maybe 5, 9, 6, 8, and we have another matrix C, which is 4, 3, 1, then we have 6, 7, 2. Now look at those 3 matrices. There is A, which is 4, 5, 6, 7, and then B, and then we have C. Look at their orders. Be sure you can be able to say the orders of A, B, and C. The order of A, this one is a 2 by 2 because it has 2 rows and 2 columns. B is also a 2 by 2 matrix because it has 2 rows and 2 columns. But look at C. It has 1, 2, 3 rows, and therefore its order is 3 by the number of columns is 2. Now addition is not possible for this to any of the other A and B because its order is different from the initial one, and therefore we cannot be able to add B to C or A to C, or we cannot even be able to subtract B from C or C from A. Those 2 operations cannot work unless the 2 matrices have the same order. Now let's try doing out this one here so that you can see what we get. Let's say, for example, now you are given, so given that A is that, B is this. Now find B plus A, that is Roman 1, and Roman 2 we have maybe A minus B. B plus A and A minus B. So what you're going to do is basically just like we work on operations. So arrange them in such a way that you're adding them. So in Roman 1, we are having this. So we are adding B to A. So we first write B. We have 5, 6, 9, and 8. Add A, which is 4, 6, 5, 7, and do the normal addition. You're going to add an element that have two elements that have the same position. For example, 5 and 4. 5 is in position first row, first column. 4 the same position. So we add them according to their positions. But if you make a mistake and add a wrong element to another wrong element, then you have it wrong. So therefore we have 5 plus 4, which gives us 9 as the answer for the B plus A. Then 9 plus 5 gives us 14. 6 plus 6 gives us 12. 8 plus 7 gives us 15. So the solution for B plus A is 9, 14, 12, 15 as that answer. Now what if we were subtracting? The same case is done for subtraction. You don't go far from what we have done here because it is a direct operation. So let's see what we have by subtracting. So Roman 2 right here. So it is B subtracted from A. So you start by writing A first. A was this one here, 4, 5, 6, 7. Then subtract B, which is 5, 9, 6, and then 8. You do a direct subtraction. Just as you do with integers is what you're supposed to do here. Now we're going to subtract what we get. So 4 minus 5, that should be a negative 1. Then 5 minus 9, it is a negative 4. We have 6 minus 6, which is 0. Then 7 minus 8, which is negative 1. So the solution for A minus B is negative 1, negative 4, 0, negative 1. So that gives us the answer for that subtraction. So be sure to subtract or add when the matrices have the same order. Otherwise, you cannot be able to add or subtract. And the next thing to look at is, first of all, I need to state that always matrices are written, the elements are enclosed in brackets. So always indicate that. Now the next thing that we're looking at is multiplication of matrices. Multiplication of matrices. Now multiplication can be in two ways. Number one, multiplying a number with a matrix, or multiplying a matrix with another matrix. Let's take an example. For example, maybe number 1, e.g. So example number 1. Let's say, for example, 2 multiplied by 4, 6, 4, 6, 9, 8. We are multiplying 2 by this matrix here, that is 4, 6, 9, 8. Now, so what we're supposed to do is basically multiplying the number 2 with each element in that matrix individually. So that gives us what? 2 times 4 is what? That is 8. You're right, 8. Then 2 by 6 gives us 12. 2 by 9 gives us 18. Then 2 by 8 gives us 16. As simple as that, you shall have multiplied a matrix and a number. Now this multiplier here, we call it a scalar. The multiplier of the matrix is called a scalar. So just like that, you've already multiplied. Now let's take an example. For example, we have this. Now we have given that. So the question is given that A is equal to 2, 4, 3, 6. Find A is that, and then B is 11, 3, 4, 1. Find 2A plus 3B. Find 2A plus 3B. So we have an example here of multiplication, given that A is equal to 2, 4, 3, 6, and B is 11, 3, 4, 1. Find 2A plus 3B. So basically you're going to substitute. So you just write the individual terms, the individual scalars and their matrices. So 2 into A is 2, 3, 4, 6, 2, 3, 4, 6. Add 3, which is multiplied by 11, 4, 3, 1. So when you open these brackets by multiplying what is inside the brackets, what do we get? So that one is equal to 2 times 2 is 4, plus, not plus rather, so 2 times 3 is 6, 2 times 4 is 8, 2 times 6 gives us 12, plus 3 times 11 is 33, 3 times 9 is, times 3 is 9, then 3 times 4 is 12, then 3 times 1 is 3. So after getting that solution, after multiplying, now we can add the individual terms or the individual elements as according to their positions. So for example, by adding, now we have, we need to get the answer. Adding 4 plus 33. gives us the answer as what? So let me clean this part here, so that we get to do the answer. So 4 plus 33 is 37. Then 6 plus 9 is 15. We also have 8 plus 12 as 20. Then 12 plus 3 giving us another 15 here. So this is the solution for 2a plus 3b. After getting that, you shall have already obtained your solution because you have worked it out correctly. Now remember that multiplication is only possible when the the addition is only possible when the two matrices, or the number of matrices that are involved, have the same order. And remember, when I said order, I meant the number of rows multiplied by the number of columns. Now we are going to move on to something else, which is a multiplication of matrices by other matrices. So multiplication of matrices with other matrices. Say for example, part A. Now you see, when you multiply matrices, you have to be very careful when multiplying that, because there are some cases when multiplication cannot occur or cannot happen. But generally, when you are multiplying matrices, then the solution, let's say for example, you're multiplying a matrix M of order M times N, multiplying by another one of order maybe P multiplied by Q. So what will happen is the solution will be having this answer as the number of rows for the first multiplied by the number of columns of the second. So this is the solution. It will be having this number of rows and the number of columns. Remember, this is the order of the first matrix and the order of the second matrix. However, it is not in every case. Let's take an example. Let's say, for example, you are given the matrix P as 4, 5, 6, 7, and then you have Q 4, 5, or the 4, 8, 9, 2. And now you are asked to multiply P and Q. So when multiplying P and Q, the solution will be multiplying Q and P. So you pre-multiply. Pre means start with. You're going to start with 4, 8, 9, and 2, multiply by. You put them side by side. 4, 6, 5, 7. Now when multiplying, you have to be very careful, because you have to ensure that you do the correct multiplication, because if you don't do it correctly, you'll get it wrong. Now usually when multiplying, we multiply the row against the column. Row multiplied by column. I repeat, row multiplied by column. Let's see. So in this case, it will be as we add, of course. So what answer do we get? So it is 4 multiplied by 4 plus, let me write it here. The solution will be 4 multiplied by 4 plus 9 times 5. Four multiplied by 4 plus 9 times 5. This will give us the element of the solution matrix. So be sure that you do it correctly, row against column. So 4 times 4 is 16, 16 plus that. Okay, let's move on to the next one, then we'll get the solution. So this second term here, the second term will be this row against the second column. So the first row against the second column will be giving us the second element on the right. So that will be 4 times 6, 4 times 6 plus 9 times 7. I repeat, it is first row against the second column, so that you are able to get the element that is occupying this position here. Moving on to the next one, we have 8 times 4. Now this one will be now second row first column, second row, first column, second row, first column. That will be giving us the element that will be occupying that position right there. That will be 8 times 4, add 2 times 5, 2 times 5. Then the last one will be second row, second column. That will be 8 times 6 plus 2 times 7. So let's see what we get when you add. Now the first one has that 4 times 4 is 16. Then we have 16 plus 45. Of course, that is 16 plus 45. That gives us 61 right here. And then we have the next one, which is 24 plus 63, which gives us 87. Then the next one is 8, that is 32 plus 10, which is of course 42. Then the last one is 48 plus 9, which is 57. Now you see what we have here is the answer for the multiplication of P and Q. And I said when doing that multiplication, you will pre-multiply Q and P. So when you're multiplying P and Q, you're not just going to write it direct, but start with Q, then multiply with Q. With Q, then you multiply with P. Then this is the solution. Be keen on how I have multiplied. It is row against column, row against column. That will give us the elements of the solution matrix. Now, given that we've done that, I want us to take a short break. When we'll be back, we'll do more on this multiplication and see why some matrices cannot be multiplied with others. Stay tuned, don't go away. Welcome back, dear learner, to the program Knowledge Quest. Just before we went for a short break, we were doing multiplication of matrices, and we were able to work out multiplication of a 2 by 2 matrix with another 2 by 2 matrix. And I said I'm going to point out some matrices, why some of the matrices cannot be multiplied to get a solution. Let's say, for example, we have matrix A, which is 2, 3. And we have matrix B, which is maybe we have 2, another matrix B, which is 3, 4. Now look at that. We have 2, 3, and 3, 4. For you to be able to multiply AB, in fact, it's not possible because we cannot be able to multiply row against column, because this one has 2 columns, this one has only one. It has 1 row, and this one also has 1 row. But we need the the row against column thing to work, because this will be multiplying 2 by 3, but what about 3? It will not work. So that will prompt us to transpose this one here, to transpose. Then we can multiply. Now, what is transposing? Transposing is basically making the row a column and the column a row. For example, this one has 1 row, so we're going to make this row to be a column. Then we can multiply. So what we'll get is 2, 3 multiplied by 3, 4 written as a column. So this way now we can be able to multiply. That is 2 by 3 plus 3 by 4. So that will be 2 by 3 gives us 6 plus 2 by 3 by 4, that is 12. So it is 6 plus 12, which gives us 18. Now somebody will ask, does it mean 18 itself is a matrix? Yeah, the number 18 is a matrix, a matrix of order 1 by 1. Now look at that. We said that when you multiply 2 matrices, let's say for example matrix A has an order of m n, and the next one has p Q. This is the order. Then the solution matrix. The solution matrix will have an order of MQ, the number of rows of the first one to the number of columns of the second one. Let's see. This one has one row, and this one also has one column. So that's why we're saying a 1 by 1 matrix. Now, after looking at that, now I want us to look at something that is very important, and it is known as identity matrix. But on this multiplication part, be sure to work more on this multiplication by doing more examples. Remember, it is row against the column. But I want us to look at identity matrix. Now, identity matrix is a matrix whereby the rows and the columns have zeros and ones. Let's say, for example, a 2 by 2 identity matrix has this one. It is 1, 0, 0, 1. Now, this is an identity matrix, identity 2 by 2 matrix, because there is a 1, there is a 0, a 0, 0, a 0, 1. Only zeros and ones make an identity matrix. Only zeros and 1 make a matrix identity. But then, not just any, because not just any arrangement of the ones and the zeros. There is this diagonal here. There is this diagonal. That diagonal, we call it the leading or simply primary diagonal. The second one will be the secondary diagonal. So for us to say that an identity, a matrix is identity, we say that the leading diagonal has ones while the other diagonal has zeros. Now let's say, for example, we have this one here, a 3 by 3 identity matrix. Let's see how it looks like. So we have 1, 0, 0, 0, 1, 0, and then 0, 0, 1. Look at that. The leading diagonal has ones, but the rest of the diagonals have zeros. The rest of the spaces have 0. So we are going to, this one is an identity matrix that is of order 3 by 3. Now, what happens when you multiply an identity matrix with another matrix that is not an identity matrix? So let me take an example of a 2 by 2 identity matrix, maybe A, which is 1, 0, 0, 1. Now let me indicate it as I to mean identity. And we have B, which is 4, 3, 2, 1. So let's try multiplying I and B. Let's try multiplying I and B. So we have 1, 0, 0, 1 multiplied by 4, 2, 3, 1. 4, 3, 2, 1. Let's see. So when you multiply these two, what do you get? I said it is row against column. So it is 1 times 4 plus 0 times 2. So 1 times 4 is 4 plus 0 times 2 is 0. So we have the answer right there as 4. Then it is row against the second column. First, row against the second column to get the second element. So it is 1 times 3 gives us 3. Then 0 times 1 is 0, so gives us a 3 at that point. And then we have 0 times 4 is 0 plus 1 times 2 is 2 plus 0 is 2. We have it right there. And then we have the second row against the second column. So 0 times 3 is 0 plus 1 times 1, which gives us 1. So look at that. Look at this solution matrix and B. The solution matrix and B, they have the same elements. They are equal. Basically, we call them equivalent. So if a matrix is in such a way that, so if A multiplied by I is equal to A, then I is identity matrix. The same can be when you pre-multiply I and A. So basically the identity matrix, it's like multiplying a number by 1. You get the same answer, like 10 times 1, because the value of the identity matrix is 1. Basically it is 1. But now I want us to look at something that is next, which is we call the inverse of a matrix. And I want you to pay very close attention to this one here, because it requires you to, of course, to borrow the concept of identity matrix and work on it. But then first of all, it's inverse. Not really inverse, but first the determinant. Let's talk of the determinant of a matrix. Determinant of a 2 by 2 matrix. Determinant of a 2 by 2 matrix. Now let's say, for example, we have 4, 9, 8, and 6. And you are told to determine, let me not use the numbers first. Let me use letters, then we can have an example. Let's say, for example, A, B, C, and then D. We have that matrix, let's call it maybe A. And you are told to determine the determinant of this matrix A, B, C, and D. Now the determinant of A, now I'm using DET to represent determinant of A is obtained as an expression. Now we have this leading diagonal. I had indicated earlier that the elements in this diagonal right there, they are in the diagonal known as the leading diagonal. So if we are supposed to find the determinant of a matrix that is a 2 by 2 matrix, the first thing is multiply the elements in the leading diagonal. So in this case it is AD. Then subtract the product of the elements in the secondary diagonal or in the other diagonal, like for example B times C, BC. I'm repeating, to get the determinant of a matrix, a 2 by 2 matrix, we first of all get the product of the elements in the leading diagonal, then subtract the product of the elements of the other diagonal or the secondary diagonal. If for example now we have this 4, 9, 6, 8. We're supposed to find the determinant of that. So the determinant of, let's say, B, so the determinant of B will be equal to AD. So it is 8 times 4 minus 9 times 6. That should be equal to what? 8 times 4 is what? 32. Subtract. 9 times 6 gives us 54. So when you subtract those two, what do you get? So it is 32 minus 54, which gives us negative 22 as the determinant of matrix B. I'm repeating a slight concept here that to get the determinant of a 2 by 2 matrix, you basically need the product of the leading diagonal, subtract the product of the element in the other diagonal. Let's get another example. Get the determinant, find the determinant of I. We have I being equal to 1, 0, 0, 1. So the determinant of I. Now, if you remember very well that 1, 0, 0, 1 was an identity matrix of order 2 by 2. I said an identity matrix has 1s in the leading diagonals and 0 in the other position. So in this case, the determinant will be 1 multiplied by 1 minus 0 times 0. That gives us 1 minus 0, which gives us 1. So you should be able to know that from today that the determinant of a 2 by 2 matrix is 1. A 2 by 2 identity matrix is 1. Always, in fact, always for identity matrices, they have a determinant of 1. But that was not the point that I wanted to drive. I want us to look at what we call the inverse of a 2 by 2 matrix. Inverse of a 2 by 2 matrix. As we wind up, inverse of a 2 by 2 matrix. Now, if we have A, now if we have a matrix, maybe A and B, if A and B are matrices, B is the inverse of A if, when multiplied, the solution is an identity matrix. If the solution is an identity matrix, that is, if you multiply A and B such that the answer is an identity matrix, then B is an inverse of A. Now, let's take an example. Let's say, for example, A is a 2 by 2 matrix with these elements 6, 7, 5, 4. Now, you're supposed to find the inverse of A. Now, let's see how we're supposed to go about it, and then find the inverse of A as we multiply to see whether it gives us an identity. Now, the first thing, very first thing, when working out the identity, or rather the inverse of a matrix, first thing is determine the determinant of that matrix. So the determinant of A, remember the formula, it is the leading diagonal, the product of the leading diagonal subtract the product of the other diagonal. That will be 6 times 4 subtract 5 times 7. That gives us 24 minus 35, which gives us negative 11. Now, after getting the determinant as negative 11, so we have it as the determinant, that is, the matrix A was 6, 4, then 5, 7. After getting the determinant, that is negative 11, the next thing now we're going to get is now the inverse, which we write as A raised to that negative 1, is going to be 1 over the determinant of A into. Now we're going to interchange the elements of the leading diagonal. We interchange so that we have it as 4, 6, and then the other diagonal we change the sign, because when it is positive it becomes negative. If it was negative it becomes positive. So this one is negative 5, negative 7. But what was our determinant? It was negative 1, negative 11 rather. So we have it as negative 11 right there. So after getting that as that, if we open this bracket, let's open it and see. Negative 1 over 11 times 4 gives us negative 4 over 11. Then negative 1 over 11 times negative 5 gives us positive, because it is a multiplication, or rather it is a multiplication of negatives. And then we have negative 1 over 11 multiplied by negative 7 gives us positive 7 over 11. And we have negative 1 over 11 by 6 gives us 6, negative 6 over 11. So after getting that, now the inverse of A is giving us negative 4 over 11, 7 over 11, 5 over 11, and we have negative 6 over 11. That is what we get as the inverse of A. But we said that an inverse of a matrix is when you multiply the two and you get the solution as the identity matrix. So what you're going to do is basically multiply A to A inverse. So after multiplying, we should be able to get an identity matrix right there. So let's see. So we're going to multiply A and A inverse. So basically A inverse rather multiplied by A, which is going to be negative 4 over 11, 7 over 11, 5 over 11, negative 6 over 11. We multiply by 6, 5, 7, 4. So when you multiply that, what do you get? Let's see. So what we get is now negative 4 over 11, of course it is row against column. So that is equal to negative 4 over 11 times 6 is negative 24 over 11 plus 7 over 11 times 5 should be giving us 35 over 11. And then we have first row, second column, so it's negative 4 over 11 times 7. It's giving us negative 28 over 7 plus over 11, sorry, over 11 plus 7 over 11 plus 4 is 28 over 11. Then 5, now row against column, so 5 over 11 times 6 gives us 30 over 11 plus negative 6 over 11 times 5 is negative 30 over 11. And then we have now the last part, which is second row, second column. So 5 over 11 times 5 gives us 35 over 11 plus negative 6 over 11 times 4 is negative 24 over 11. Now let's work that out. Gives us negative 24 over 11 plus 35 over 11 is positive 11 over 11. Then 28, negative 28 over 11 plus 28 over 11 is 0. Then we have 30 over 11 minus 30 over 11 is 0. And then the last one, 35 minus 24 is 11 over 11. So what do we get? This is the same as writing 1, 0, 0, 1. That tells us that the answer that we got here, this one here, this answer as negative 4 over 11, and this one, this is the inverse of A. This is the inverse of A, because when you multiply the two, you get an identity. That tells you that you've already obtained the inverse of matrix A. Now, be sure that you remember how to work out the determinant, because that is the important part of the working out the inverse, and then interchanging the rows as you interchange the signs. Rather, you change the signs of the other diagonal. Otherwise, I want us to stop there, but then the next time in the next class, we'll be able to look at more questions on this matrices topic. Until then, stay tuned and God bless you.